Hello and welcome to Controllers Tech. In part 1 of this series, we covered the RTOS configuration and ran a single LED blinking inside one task. But real embedded systems need more than that. They require several independent jobs running simultaneously, each with its own priority, its own timing, and its own dedicated role in the system. That is exactly what this part 2 is all about. In this video, we are going to create multiple tasks, assign priorities to each of them, and control the task lifecycle using the CMSIS-RTOS API. We will also see how a high priority task can preempt a lower priority one, and why the reverse is simply not possible. Before we dive into the code, let me give you a clear picture of what we will be doing in this video. I am going to create 4 different tasks, each with a different priority level. Task 1 will blink one LED, and will have the lowest priority of the 4. Task 2 will blink a second LED, and will have a priority higher than Task 1. Task 3 will blink a third LED, and its priority will be higher than both Task 1 and Task 2. Task 4 will control the life cycle of one of the remaining tasks, and it will hold the highest priority of them all. First, we will observe what happens when Task 1 is performing a long operation. We will check whether the higher priority tasks are able to preempt it and continue blinking their LEDs at the predefined rate. After that, we will intentionally delay the processing of Task 3 and observe whether Task 1 and Task 2 can preempt it and blink their LEDs at the desired rate. For this tutorial, I am going to continue building on the project we created in the previous video. Here you can see the RTOS Part 1 project already loaded in STM32 Cube IDE. The first thing we will do is rename the project to Part 2. Make sure the Update References checkbox is checked, so the project name gets updated in all the required places as well. The renaming is done. Now let us delete the previously generated configuration, and I will also rename the IOC file accordingly. With that, everything is properly set up for Part 2. Before we begin configuring the project in Cube IDE, let us take a quick look at the schematic of the STM32 Nucleo-L496 development board. As mentioned in the previous tutorial, the blue LED is connected to pin PB7, and we will continue using this LED today. In addition to the blue LED, the board also features a red LED, which is connected to pin PB14. We need 3 LEDs for this project. The third one is a green LED, which is connected to pin PC7. So now we have all 3 LEDs ready, one for each of the 3 tasks. Let us open STM32 Cube MX and load our Part 2 project. As mentioned earlier, this is essentially the Part 1 project with only the name changed to Part 2. Pin PB7 is already configured as an output. Let us rename it to Blue LED so that it is easier to identify while writing the code. Next, let us set pin PB14 as an output as well, and rename it to Red LED. Similarly, pin PC7 will be set as an output and renamed to Green LED. With that, all 3 LED output pins are now configured. Let us navigate to Middleware, then FreeRTOS, and open the Tasks tab. In the previous project, we only had one task, which was the default task. I am going to rename it to Task 1 and set its priority to low. Now, although I could use below normal, since below normal is technically lower than normal priority, I am using low here just to keep the naming consistent and easy to follow. The stack size will remain at 128 words, and the entry function will be renamed to Start Task 1. Now we will create the remaining tasks in the same way. Click the Add button to create a new task. I will name this as Task 2 and set its priority to below normal. This priority is still higher than Task 1, which is set to low. Next, we will add another task, name it Task 3, and set its priority to normal. All tasks are kept at a stack size of 128 words. Since we do not need to perform heavy operations inside them, we are simply blinking LEDs. Finally, task 4 will be created with a priority of above normal, and its stack size will also remain at 128 words. So now we have 4 tasks in total. To summarize the priority order, task 1 has the lowest priority set to low, followed by task 2 at below normal, task 3 at normal, and task 4 at above normal, making it the highest priority task of them all. If you check the FreeRTOS heap usage section, you will see that all 4 tasks occupy the same amount of memory, and we still have 472 bytes remaining. This is more than sufficient, so no changes are needed here. Let us now click Generate Code to generate the project files. Alright, with that done, let us head back to STM32 Cube IDE. As you can see, all 4 task functions have been created inside the main function. Now it is time to write the actual code inside each of these tasks. Instead of manually setting and resetting the pin state, I am going to use the toggle pin function, which automatically switches the pin between high and low with each call. Inside task 1, we will toggle the red LED, with a delay of 1 second. Keep in mind that task 1 has the lowest priority of all 4 tasks. Inside task 2, we will blink the blue LED with a delay of 500 milliseconds. Similarly, inside task 3, we will blink the green LED with a delay of 200 milliseconds. We will leave task 4 unchanged for now, as we know we will be modifying it in a later step. Let us first test what we have so far. We will build the project. There are no errors, so let us go ahead and flash it to the board. As you can see, all 3 LEDs are now blinking on the Nucleo board. You can focus on one LED at a time to observe each one individually. You will notice that the red LED blinks every 1 second, the blue LED blinks every 500 milliseconds, and the green LED blinks every 200 milliseconds. All 3 tasks are working correctly, each blinking its respective LED at the predefined rate. Now we will take this a step further. We are going to block the processing of task 1 and observe whether task 2 and task 3 wait for it to finish, or whether they preempt it and continue blinking their LEDs at the defined rate. Inside task 1, I am declaring a variable called wait and initializing it to 50 million. After the delay, the code enters an empty while loop that keeps decrementing this variable on every iteration until it reaches 0. During this entire time, the CPU is stuck inside this loop, doing no useful work. It is simply burning through clock cycles waiting for the counter to hit 0. This simulates a situation where a low priority task is hogging the CPU with a long blocking operation. Now let us see whether this empty while loop inside task 1 has any impact on task 2 and task 3, or whether they continue to perform their operations as expected. Let us flash this updated project to the board. As you can see, the red LED is now blinking at a slower rate than 1 second. This confirms that the empty while loop inside task 1 is directly affecting its own blinking speed. However, the blue and green LEDs are still blinking at their predefined rates, the blue LED every 500 milliseconds, and the green LED every 200 milliseconds. They are completely unaffected by the empty while loop we added inside task 1. So why does this happen? When task 1 gets stuck inside that empty while loop and task 2's delay expires, task 2 simply preempts task 1, performs its job, and goes back to the blocking state. The same applies to task 3, it does not need to wait for task 1 to finish. It preempts task 1, blinks its LED, and returns to blocking. This is because task 2 and task 3 both have higher priorities than task 1. They do not need to wait for task 1 to enter the blocking state on its own, they can interrupt it at any point, complete their operation, and step aside. Task 1, on the other hand, can only run when both task 2 and task 3 are in the blocking state. That is why task 1 is still running, but at a much slower rate than before. Now let us move that empty while loop into task 3 and see what changes. Since task 3 has the highest priority among the 3 LED tasks, task 1 and task 2 cannot preempt it. So if task 3 gets stuck running that empty while loop, task 1 and task 2 have no choice but to wait until task 3 is completely done. Let us flash this updated code to the board. As you can see, all 3 LEDs appear to be blinking together. Let me explain exactly what is happening here. Task 3 toggles its LED and immediately calls OS delay, which puts it into the blocking state for 200 milliseconds. During that window, task 1 and task 2 get their turn to run, and they both toggle their LEDs on. However, since task 3 only has a 200 millisecond delay, it wakes up first and preempts both task 1 and task 2. At this point, the LEDs of task 1 and task 2 are still on, and both of those tasks are now sitting in the background, waiting for their turn. Task 3 is now running the empty while loop. Task 1 and task 2 are ready to run and want to toggle their LEDs off, but they cannot. Task 3 is still executing and holds a higher priority. They are forced to wait. Once task 3 finally finishes the loop, it toggles its own LED off and calls OS delay again. During that 200 millisecond blocking period, task 1 and task 2 finally get control and toggle their LEDs off as well. Then task 3 wakes up once more, preempts them both, and the entire cycle repeats from the beginning. Because task 3 holds the highest priority, task 1 and task 2 are forced to synchronize with it. They can only run during the periods when task 3 is in the blocking state. And that is the key takeaway from this demonstration. A higher priority task can preempt a lower priority one at any point in time, but a lower priority task can never do the same in return. Now we will leave task 3 as it is and use task 4 to demonstrate how to control the life cycle of a task. Inside task 4, I am calling OS thread suspend to suspend task 3, then waiting for 5 seconds, and then calling OS thread resume to bring it back. Since task 4 has the highest priority of all, it can preempt task 3 even while task 3 is stuck running its empty while loop. This means as soon as task 4 gets its turn to run, it will suspend task 3 immediately. When a task is suspended, it is completely removed from the scheduler and will not receive any CPU time at all. However, its stack and internal state are safely preserved inside the FreeRTOS kernel, meaning the task still exists in memory. It has not been deleted. It has simply been taken off the scheduling timeline until something explicitly resumes it. Let us flash this to the board and observe how it behaves on the Nucleo board. As you can see, the green LED stays on for quite a long time. Here is what is happening. When the green LED turns on, task 3 enters its empty while loop, and while it is still running that loop, task 4 preempts it and suspends task 3 for 5 seconds. Task 3 is now paused with the green LED left in the on state, and it will remain exactly like that until it is resumed. While task 3 is suspended, task 1 and task 2 are free to run without any interference. You can now see the red and blue LEDs blinking at their normal rates again. Once task 3 is resumed, it will toggle the green LED off and start running the empty while loop once more. Task 4 will then preempt it again and suspend it for another 5 seconds, during which task 1 and task 2 can continue running freely. So using suspension and resuming, we have full control over when a task runs and when it is completely taken out of the picture. When task 3 is suspended, it is no longer part of the scheduling timeline, which allows task 1 and task 2 to run as if task 3 does not exist at all. Now, alongside suspension, there is another important function called OS thread terminate. Unlike suspension, this function completely and permanently removes the task from the system. Once a task is terminated, it cannot be resumed, you would have to create it all over again from scratch. Because of this, task termination is rarely used in practice, and suspension is generally the preferred approach when you need to temporarily stop a task. One case where termination does make sense is when a task is only meant to perform a one-time initialization at startup, and then remove itself from the system once that job is complete. In addition to what we use today, CMSIS-RTOS version 2 provides several other functions that give you a more detailed view of what is happening inside FreeRTOS at runtime. Here is a quick overview of some of the commonly used thread functions available. OS thread getID returns the ID of the currently running thread. OS thread getState allows you to query the current state of any thread at any point, whether it is running, ready, or blocked. We already used OS thread suspend and OS thread resume in this video. Suspend removes a thread from the scheduling timeline until something explicitly brings it back, and resume does exactly that. It places the thread back into the scheduler so it can run again. OS thread terminate permanently deletes a thread and frees the memory it was using. As discussed earlier, once a thread is terminated, it is gone for good, and cannot be brought back without recreating it. Finally, OS thread get priority reads the current priority of a thread, and OS thread set priority allows you to change that priority at runtime. This can be particularly useful in situations where the importance of a task needs to shift dynamically based on the current conditions of the system. We will be covering all of these functions in greater detail in the upcoming parts of this series, so make sure you stay tuned for that. So to summarize what we covered in this video, we saw how multiple tasks work in an RTOS, how priorities determine which task gets CPU time, and how we can control the lifecycle of a task using suspend and resume. We also saw preemption in action, where a higher priority task can interrupt a lower priority one at any time, but a lower priority task can never do the same in return. That is it for this video. You can download the complete project from the article linked in the description below. If you have any questions or doubts, feel free to leave them in the comments section. Keep watching, and have a great day ahead.